Introduce our next speaker, Tobias from Saarland University, who will talk on the Dyson equation for two positive maps. Tobias, please.
Thank you very much for the introduction, and many thanks to the organizers for inviting me and giving me the opportunity to speak here. So it's really a great pleasure also for me. So yes, I'm going to talk about some recent work which I carried out during the last months, let's say. It's not yet on archive, but I hope that this will happen soon. So yeah, it's on the Dyson equation for two positive maps. And well, as the title suggests, to people which already know something about free probability, that this might have to do something with free probability. And to those people, it will certainly not come as a surprise that non-commutative function theory plays also a great role in, well, it's well known that non-commutative function theory plays an important role in especially the operator-valued theory of free probability theory. And somehow the idea of this talk is to show that somehow techniques from non-commutative function theory also apply when tools from free probability fail. That's somehow what is hidden behind the word two positive. But I will be more precise in some minutes. But first of all, I should maybe introduce or give you a kind of motivation why this kind of question should actually be interesting to you. And a good starting point actually is the connection to random matrix theory. So let me start with the motivation coming from GUE matrices and actually evaluations of affine linear pencils in GUEs. So let's get started with the most basic definition of a standard self-adjoint Gaussian random matrix. By this I simply mean, well, a random matrix with Gaussian entries. Complex Gaussian entries. So just think of a matrix where the entries are Gaussian random variables, complex ones such that the real and imaginary part are Gaussian random variables, and they are centered, and the variance is normalized in such a way that we somehow have mean 0 and trace 1. The trace of the square of the matrix is 1, so a kind of variance 1 assumption which we have behind the scenes. So this is one of the most basic random matrices, and we know that in the normalization is as such that in the limit, if n goes to infinity, we see a nice limit law for the eigenvalues of such matrices. Namely, this is the famous Wigner semicircle law. But we will not deal with only one of such random matrices. We will actually involve more of them. And as soon as you have more of these random matrices, you can start producing more complicated random matrices out of them. And here is the following random matrix model, which played a crucial role in the work of Hagerup, Torp-Jonsson, and also the work of Hagerup and Torp-Jonsson with Schulz. It says that we take now independent self-adjoint Gaussian random matrices where each x1n up to xn, capital N, is a self-adjoint Gaussian random matrices, and all of them are chosen to be independent. And then we take somehow coefficient matrices, self-adjoint and complex, of some dimension m times m, and then we just tensorize them and put the deterministic matrices as coefficients in front of the matrices of our Gaussian random matrices like this, and then we add also some constant part by just tensorizing B0 with the identity, and this gives us a kind of block random matrix if you want. And the question is, can we understand the behavior, the large n limit for the eigenvalue distribution of such matrices? And so let's first make it precise what I mean by the empirical eigenvalue distribution. So by this I simply mean whenever we have a random matrix, independent of the particular choice of the particular structure this random matrix has, we can just say, okay, if it's a self-adjoint one, it has random eigenvalues, and we just produce a measure out of these eigenvalues by just putting atoms at each of these eigenvalues and weighting them with 1 over the dimension in order to have a probability measure. And this is what we call the empirical eigenvalue distribution. And then we have our matrices of the form I introduced on the previous slide. And now let's look at a concrete example. So it might look, for instance, like this. So we have here again, our self-adjoint Gaussian random matrices, which are chosen to be independent. Yeah, I actually forgot to write this down here. Of course, they should be independent as before. And then I just decorate them with coefficient matrices like this. And all these matrices, as we assumed at the beginning, are self-adjoint. And this produces a new 3n times 3n random matrix. And we may ask, okay, can we understand the asymptotics of the eigenvalue distribution? So first of all, it's maybe good to look at a concrete example. So we just choose one dimension n, a large dimension that you like. We just produce we just compute the eigenvalues and put a histogram. And this is how it looks like. So it seems that if n is large enough, this eigenvalue distribution seems to have a nice shape. And we would like to know, can we compute this this limit shape, this limiting eigenvalue distribution? And the answer is yes, we can do this by means of free probability theory, and especially by tools from operator-valued free probability theory. And this is what allows us to compute this red curve shown in the picture. So the question is, how does this work? So how does free probability help us to compute this limiting curve? And in fact, well, in order to do this, I should first tell you a little bit about the basics of operator-valued free probability and of free probability in particular. And I will do this here on this slide. So free probability, as probably some of you know, is just well, a non-commutative generalization or a highly non-commutative analog of classical probability theory, where the underlying structure is modeled, or the underlying object is a non-commutative probability space. By this I mean just an algebra. This is somehow the analog of the algebra of random variables, and a phi which plays the role of the expectation. But here we just forget about this classical probability language. We just talk about the setting, an algebra, and a unital algebra, of course, and a unital linear functional phi defined on that algebra. So here it comes. So A is a unital, and we restrict here in this situation to the case of C-star algebras. You can also do it for Neumann algebras, or you can just do it in more algebraic terms. But here the C-star algebra framework is the right one. So we have a unital C-star algebra, and this simply means we have a unit element sitting inside A, of course, and the unit element is going to be denoted by one index A. And the phi, as I said before, is the replacement of the expectation. And in our situation, in the case of a Z-star algebra, a Z-star probability space, we require this phi to be a state, namely a positive linear map satisfying this normalization that the identity in A is set to 1. And we refer to this as the expectation on A. Okay, and then there are some analytic tools. I mean, this was just a very brief introduction into the basics, or the basics of non-commutative probability theory. Free probability comes in addition with the notion of free independence, but I would like to be quite vague here. So I'm just saying that this is a kind of highly non-commutative analog of classical independence. This is sufficient for what follows. But what is important in the sequel is that we have some huge analytic and powerful analytic machinery to deal with free independence and with all, well, with non-commutative random variables and so on. And this is like in classical probability, the Fourier transform, the Cauchy transform in free probability theory. And by this, I mean simply a holomorphic function defined on the complex upper half plane and taking values in the complex lower half plane, defined in this form. So we just take the resolvent of our self-adjoint operator. So in this case, X should be a self-adjoint operator for simplicity. And then we just, we know that this resolvent exists and we apply phi to it. And then it can actually be written in terms of, well, as an integration of this resolvent function with respect to some measure. And this measure we call the analytic distribution of this operator X. So this is the analytic theory of scalar-valued free probability. And how does operator-valued free probability look like? The whole philosophy, well, basically the philosophy behind is that you replace the scalars the complex numbers by another unitarily embedded sub-C-star algebra of A. So let's say again, A is a C-star algebra and B is now a unital C-star subalgebra, which contains, I mean, unitarily embedded in the sense that it contains the unit element from A. And so this explains what the A is, and we specify the B here as this algebra, this underlying C-star subalgebra. And then the expectation is now a conditional expectation, namely a completely positive map defined on A and taking values in B. And it satisfies the property that it behaves like the identity on B, and it has this bimodule property that if I multiply an element from A, from the left or from the right by elements coming from B, I can just move them out. So these are the properties that I need. And whenever such a thing is given, I call this an operator valued C-star probability space. And interestingly, you find analogs for all the things which I've shown you in the left column. There's also an upper half plane. Namely, I just collect all the elements in B whose imaginary part is positive, is a positive operator and invertible. And in the other case, in the lower half plane case, I put a minus sign in front, and the imaginary part is defined like this, just B minus the adjoint of B divided by 2i. So the very canonical thing. And there's also an analog of the Cauchy transforms. And here we do basically the same. We just take, we follow the philosophy that the complex numbers are replaced by elements from B. So what we do is we just take the resolvent, the resolvent in B minus X, and then we apply the expectation to it. And this can be shown to be a map from the upper half plane in B to the lower half plane in B. This is now, of course, a more complicated object because we have this B involved. It's not a scalar half plane, but it shares many or has many properties like the scalar valued one. And by this, you can build up operator valued free probability very much in parallel to the scalar case. Okay, so this on the basics. And now having this in the background, we can look a little bit closer at our problem that I mentioned at the beginning. Remember that we had standard self-adjoint Gaussian random matrices, and we put them into a fine linear pencil and wanted to understand the limiting behavior for the eigenvalues. And the fundamental observation is what happens actually with one random Gaussian random matrix. And this is the famous Wigner semicircle law, which states that in the limit, the eigenvalue distribution is given by the semicircular distribution. So whenever I take one such standard self-adjoint Gaussian random matrix, then these integrals with respect to the empirical eigenvalue distribution converge under the expectation to the corresponding integrals with respect to the semicircular distribution. But in fact, this can be improved and was improved to an almost sure convergence. So you can just drop the expectation and you still have this phenomenon. And this, in terms of the histogram, simply means that you don't have to take the average over more realizations of your random matrix in order to see this limiting behavior. You can just do it for once and typically for one realization, and typically you see this behavior here. And in order to go a little bit further, we just replace, because now we have this free probability language in the background, we can just replace the semicircular distribution by an operator which has precisely this distribution, namely the semicircular distribution, and such an operator is called a semicircular element. So here I'm just saying that this Wigner semicircle law simply says that the trace, the normalized trace of a polynomial in my Gaussian random matrix converges to the same polynomial evaluated in the semicircular element under the expectation almost surely. So it's precisely the same result. All I did is just rephrasing the right-hand side, this integral, with respect to the semicircular distribution as the expectation of a polynomial in a semicircular element. Okay, why did I do that? The point is that with this formulation, one can actually go to the multivariate case, and one can state the famous result of Voiculescu on asymptotic freeness of the self-adjoint Gaussian random matrices. And it says that if now I'm taking n tuples of independent standard self-adjoint Gaussian random matrices, as we did at the beginning in our case, remember, then the same result remains true, but with polynomials replaced by non-commutative polynomials. So it's quite clear what I mean by a non-commutative polynomial, but just to be as clear as possible, I simply mean a non-commutative polynomial in variables, formal variables x1 up to xn is a linear combination of words of any length in my letters x1 up to xn. And this is what I call a non-commutative polynomial. And the statement of Voiculescu says that I have somehow the same result as before, but now, as I said, with commutative polynomials replaced by the non-commutative polynomials. And again, it was shown that one can drop the expectation and just and gets almost sure convergence. And in the limit, I mean, I should say this, that the semicircular elements which I get here in the limit, they are not general. They are in somehow general position. They are freely independent. I mean, that's somehow the crucial message here, that free independence describes the limiting behavior of independent Gaussian random matrices. So in this sense, free independence comes up or shows up naturally in the large n limit of classical independence. That's somehow the philosophy. And it tells us that if we understand semicirculars, freely independent semicirculars, we understand the behavior of Gaussian random matrices. And with this result at our hands, we can look back at our initial example. Remember that the model we were interested in looks at this, like this. We have a random matrix Xn built out of the standard Gaussian, self-adjoint Gaussian random matrices. We consider the independent ones, built out of them like this. So we decorated them, well, basically by the Kronecker tensor product with self-adjoint deterministic matrices as coefficients. And having this result here, it's quite easy to check that this implies that for our new model here, we have this behavior here. So it tells us that under the trace, I have an almost sure convergence to the trace of a polynomial evaluated in another operator, which is now built out of the semicircular elements, which describe the behavior of these matrices here. And it basically looks like it has basically the same form. All I'm doing is I'm just replacing the n by n identity matrix by the one in the algebra where my semicircular elements live in, and I replace the x1n by s1 and up to the xn capital N by sn. And in this way, I get another operator, and this turns out to be an operator-valued semicircular element. I have not yet defined what an operator-valued semicircular element is, but I just want to mention this name already at this point. It simply says that it has a very interesting structure, a structure which can be studied by means of operator-valued free probability theory. And this gives us hope to solve our initial problem. And indeed, it is precisely what solves the problem. Namely, we observe that the limiting the empirical eigenvalue distribution converges weakly, almost surely, if n goes to infinity, to the analytic distribution of this operator-valued semicircular element. So all I'm doing is I'm considering a measure mu s, which is defined by this condition here. We simply require that the trace of the polynomial evaluated in my operator-valued semicircular element is the same as integrating the polynomial with respect to this measure. So this is what defines the analytic distribution of this operator. And what I'm saying is that this object is the object of interest because it describes the limiting behavior of the empirical eigenvalue distribution of the operators of interest. Okay, and now it's maybe time to look at the operators, or at the operator-valued semicircular element a little bit closer. So what do I actually mean by this? first of all, let me be a little bit more precise in the sense that I'm saying that it's an operator-valued semicircular element with mean B0. So remember, B0 was the coefficient in front of the identity matrix. So it's this one here. This gives the mean. And I have also a covariance, which in this operator-valued setting turns out to be, or should be, a map from the M by M matrices to themselves. And they are defined in this form. So I'm just subtracting from my operator-valued semicircular element its mean, and then I'm considering somehow the trace or the conditional expectation of the square of this operator. But in between, I put in a matrix, just some general matrix B, and this induces me or gives me a mapping from the M by M matrices to the M by M matrices, and this mapping here, the covariance mapping, encodes basically all the properties that I need to understand this operator-valued semicircular element. And if you carry out the computation, you will see that this eta looks like this. So you just take the coefficient matrices and multiply them from the left and right to the matrix B at which you are evaluating your eta. So this is this particular form. And the question is, what does this tell us? And it tells us actually a lot, because since we enter the business of operator-valued free probability, and since we are dealing with an operator-valued semicircular element, operator-valued free probability theory teaches us that the operator-valued Cauchy transform, so this is the object that I introduced before, and in the case of this operator S, it looks like this. So I'm just taking the resolvent of my operator S, a kind of B-valued matrix-valued resolvent for my operator S. So it looks like this. So I'm taking here a kind of conditional expectation in the sense that I'm only applying the trace to the entries coming from the underlying algebra, and I leave the matrix structure. And the point is that this function solves the so-called Dyson equation. It's a kind of quadratic equation for the Cauchy transform. And so now you see where the Dyson equation enters the picture. And the point is that this matrix-valued Cauchy transform, if I just apply it at a scalar multiple of the identity, evaluate it at such a scalar multiple of the identity, and take the scalar value trace of it, I get precisely the Cauchy transform of the analytic distribution of this operator S. And this is, remember, is the object we were interested in. And hence, you can recover from this knowledge, so provided that one can solve the Dyson equation, which determines this function, the operator-valued Cauchy transform, you can, by this identity, compute the scalar-valued Cauchy transform. And from the scalar-valued Cauchy transform, you can actually recover the distribution of interest just by means of the Steedy's inversion formula. So this tells us that operator-valued free probability is really able to settle this problem. But the question is, we had this covariance map eta. So we would like to understand a little bit better what actually the role of this eta is. So what kind of properties do we need in order to get this machinery to work? And so I should maybe say a few words on the properties of this map eta. And in fact, it turns out to be a positive, and in fact, it's a completely positive map in this case. And in order to introduce or to remind you of this terminology, let me just spend this slide here. So our setting is that of a unital C-star algebra with unit denoted like this. And I define B as A to be the set of all self-adjoint elements in B, and by B plus the set of all positive elements in B. And then, as you know, a linear map eta from B to B is said to be positive if it maps positive elements to positive maps, positive elements to positive elements. And in this case, we have that these maps are automatically bounded. This is important to know. And we will denote by P of B the set of all positive maps from B to B. And as you certainly know, a K-positive map is simply a map which remains positive under amplification. So what we do is we let eta introduce a map from the K by K matrices over B to themselves, but just applying eta entry-wise to a K by K matrix. And if this map is positive in the aforementioned sense, then we call the map eta k positive, and by pk of b, we denote the set of all k positive etas. And completely positive, of course, if eta belongs to all pk of b, so it's k positive for every integer k, then we call it completely positive. And as you know, so we have descending chain of inclusions. So inside PB, we have P2 and so on. And the completely positive maps sit inside everything. And what is interesting to note is that these inclusions might be strict. So this is was shown by Choi. So the result, for instance, is that on n by n matrices, we have a strict inclusion of the n positive maps, which, by the way, are also the completely positive maps inside the n-1 positive maps. So you see that these, so moving between different levels, moving between different positivity levels really changes the situation. So there are some differences. Okay, this is certainly not surprising to you, but how can we make use of this? So the point is that now we actually generalize this, this construction that I presented to you in the random matrix case. So what we do is we just replace the matrices. So remember, this is the space, the m by m matrices, where our coefficients came from. And we just replace this coefficient space by an arbitrary C star probability space. So we say we have a unital Z star algebra with some distinguished state phi on it, playing the role of the expectation, as I introduced it before. And then the crucial step is that this data, which specified our operator valued semicircular element, namely the expectation and the completely positive map eta, this together forms a so-called data pair, and the eta that we observe or that we computed, that we obtained in the operator valued semicircular case, turns out, as we computed it, to be an operator to be a completely positive map, and so it falls into the setting of positivity. Of positive maps, and why not generalizing them to say, okay, we just take our mean to be any self-adjoint element that we like, and we take our eta, it could be a completely positive one, a completely positive map, like in the operator valued semicircular case that we studied before, but why not starting with a general positive map? So this is somehow the most general setting we might consider, and then the question is, can we make sense out of this? Can we somehow repeat this construction without an underlying semicircular operator? Because actually, in this situation, there can't be an operator which implements this eta, because if there would be one, the eta must be completely positive, but there is none. So the idea is now we take, we would like to associate to any such data pair a probability measure. So what we do is we take any tuple consisting of a self-adjoint matrix in B and a positive linear map from B to B, and we would like to associate to it a probability measure on the real line, and we do this as follows. So first of all, we take a function from the B-valued upper half plane to the B-valued lower half plane, and we take this to be the unique solution. In fact, this is already a statement that there exists a solution and that this solution is in fact a unique one of the Dyson equation. So now again, we see the Dyson equation, again, this quadratic equation. And with this solution of the Dyson equation at hand, we define our probability measure as follows. So first of all, we consider this function here. So we evaluate our solution G eta at the point Z times identity minus this mean. And then it turns out that this function here is nothing but a scalar valued Cauchy transform. It has all the analytic properties that a scalar valued Cauchy transform must have. And hence there exists a probability measure on the real line such that this function here is nothing but, a Cauchy transform, namely the Cauchy transform of this measure mu rho. And this somehow is the most abstract version of the construction that I have shown to you in the operator valued semicircular case. So, and we of course recovered this. So if we apply to the B0 and the eta in the operator valued semicircular case that we discussed before, you will get exactly the analytic, asymptotic eigenvalue distribution that we discussed previously. But now we can actually go beyond this case. So we can go beyond the case where we have an operator, an underlying operator in some operator valued C-star probability space, and we can still talk about this map. But there are some problems actually, namely, first of all, I told you here about Cauchy transforms. I said that this function here, at the left-hand side, is actually a Cauchy transform, and hence can be written in the usual form as a Cauchy transform. But for that purpose, we must be sure that the left-hand side in the argument set is a holomorphic function. And in order to get this, one should better have the G eta, this unique solution of the Dyson equation, to be a holomorphic function in an operator valued sense. And this is what requires the notion of holomorphic functions between Banach spaces. So I'm pretty sure that everyone here knows these things quite well. But just to fix the terminology, so here I'm just saying whenever I have two complex Banach spaces, and I take an open subset, an open subset in my Banach space E, and the function f defined on this open, here there should be a u, this is unfortunately a typo. So I'm considering now a function defined on this open subset u, taking values in f, and I call this Gateau holomorphic if this limit here exists, as you certainly know. For every point x in my open set and for every direction h, this limit should exist, and I call it Fréchet holomorphic if my function is not only Gateau holomorphic, but also the Fréchet derivative, which I defined above, defines a bounded linear operator, and it has this property here that it's somehow the first order term in the Taylor expansion. So this is what I'm saying here, and in this case, we define the Fréchet derivative to be just this linear map introduced by the Gateau derivative. And we just call a function holomorphic if it is Fréchet holomorphic and at the same time has some minimal amount of, contains a minimal amount of continuity, namely locally boundedness. And this simply says that for every point in my set U, I find a radius such that on the disk or the ball around this point x0 with this given radius, my function is bounded, uniformly bounded. Okay, I'm pretty sure that these things are well known to you, but with this in the back, we understand what comes next. Namely, we have this result of Helton, Rashidi, Farr, and Speicher, which says that given a positive linear map, then there exists a unique solution of the Dyson equation. And the most important what is also important is the fact that this unique solution is not only has some nice continuity properties, namely it is not even continuous, it's also a holomorphic function, and it has this nice boundedness property that the Cauchy, the norm of the Cauchy, this function, which behaves somehow like the Cauchy transform, can be bounded like the absolute value of the inverse of the imaginary part for all points in the upper half plane. So I also put my name here because that the function is holomorphic, which is important for our construction, was not made explicit. So in the paper of Helton, Rashidi, Farr, and Speicher, so you need a little a small argument to get a holomorphy out of it. So this is somehow a little contribution, a small contribution that I made here. But with this in mind, this justifies the construction that I presented to you before, because given such a data pair, we can consider this function, the function that I introduced to you before, and this function turns out to be a holomorphic function. And it has the property that this limit here at infinity is 1. And these are the characteristic properties that the Cauchy transform satisfies. So this G rho is indeed the Cauchy transform of a Borel probability measure. And this is the mu rho that I claimed to exist before. So this afterwards justifies that this construction which I presented to you really works. Okay, so now it's really time to come to the main question. So we have introduced this kind of black box, this density of state map. So this is called density of states. This goes back to a construction of Alt, Erdős, and Krüger. And it generalized it to and we generalized it to the case of, well, to the C-star case and to the case of only positive maps. So, and in this way, we have introduced a kind of mapping, and we would like to understand what actually are the properties of this map. We basically know how this construction goes. So so we know how to construct the mu rho, but it involves certain non-trivial steps. And the question is, can we somehow have sufficient good control on all these steps such that we can understand the topological properties that the mu has? And in order to talk about topological properties, we should introduce topologies on the left-hand side and the right-hand side. And on the left-hand side, this is quite easy. So we just take on the self-adjoint elements, just the norm metric coming from B. And on the positive maps just the usual usual norm on maps from B to B for all bounded linear operators from B to B. So this is easy. And on the probability measures, we take the Levy metric. So this is the metric which is known to somehow encode weak convergence. So if you have a sequence which converges with respect to the Levy metric, it also converts weakly and vice versa. And the precise definition is not important, but it just tells us that we have the right metric to talk about weak convergence, let's say. And it involves the so-called cumulative distribution function, which is defined like this. And we would like to understand the properties of this map. But in fact, in order to do that, we must restrict from positive maps to two positive maps. The reason is that we would like to have access to some analytic tools. And in order to have these analytic tools, we need some additional restriction. We need some additional condition, namely the true positivity. And what I will do in the sequel is I would like to explain to you why this property of true positivity is so important. So where does this enter the scene? And but first of all, I would like to tell you what under this condition can actually be set. And this is the main result actually that we obtain in this kind of continuity statement that I announced. And it says that given this density of, if we consider this density of state map, then we observe that it is separately Hölder continuous in the sense that if I fix my completely positive map and if I vary the self-adjoint part, then the Levy distance can be bounded by some universal constant times the difference between the self-adjoint parts to the power 1/3. And if I, on the other hand, fix my self-adjoint part and vary the completely positive, the two positive maps, I'm sorry, then I have this result here for the Levy distance with the constant C2, again, a universal constant of this form. And in fact, this is what I would like to mention is that this result here already appeared in a paper, in my joint paper with Marwa Banner, but there we actually used a kind of, well, we used an operator-valued Lindeberg method, and this was basically limited to the completely positive case. So we have such a result in this paper, but only for completely positive maps. But here the statement is that it also works for two positive maps. So we can really restrict it, that we can actually extend this result in this direction. And if you put things together, you see that with respect to any product metric on this Cartesian product here, you get a map from this topological, from this metric space to this metric space here, which at the end is uniformly continuous. So this is the result. And I would like to explain you, I mean, as I already said, I would like to tell you how non-commutative function techniques enter the scene. And this is why we need the P2 restriction. But in order to see that, let me explain what is actually the strategy behind the proof. And the strategy is that we do a kind of continuous interpolation. And I already mentioned that in my paper with Marwa, I used a discrete Lindeberg interpolation, but here we are using a continuous interpolation. So we are interpolating between the two given data pairs by an interpolating family. And we do this in the first case where the eta is fixed by linearly interpolating between the b's. And in the second case, we take a linear interpolation between the etas and leave the b0 fixed. And then the idea is, well, we just use the fundamentals of calculus. We just write the difference between the two Cauchy transforms as the integral, or we estimate it against the integral of the absolute value of the derivative. But this tells us, but in order to perform this, we should actually have some behavior on the evolution, let's say, of the Cauchy transforms, these abstract Cauchy transforms. And this is somehow what we will do in the sequel. But the question is, if one has something like this, such bounds for the Cauchy transform, can one actually go to the, or can one actually get these bounds for the Levy distance? And indeed one can, because there are some general results saying that if you can control the difference between the Cauchy transform, actually some integral over the difference of Cauchy transforms, then one can use this to derive bounds also for the Levy distance. And but again, as you can see, since we also want to integrate over the difference between the two Cauchy transforms, one really needs a good understanding of the derivative of the Cauchy transforms. So what we actually need to do is we need to understand these kind of Cauchy transforms in the first case, so where we just move where we just vary the self-adjoint part, and in the second case, we leave our B0 fixed and we vary the eta. So here the T independence comes via the Cauchy transform, this solution of the Dyson equation, and here it comes basically from the argument at which, or comes from the point at which we evaluate the Cauchy transform. And in order to do that, this is where we need non-commutative function theory, but in fact, we will need a kind of truncated version of it. I mean, it's certainly not surprising to you that this, that something like this works. But let me just give the main ingredients, what I mean by this. So by as you know, non-commutative function theory is that I'm considering non-commutative sets in the sense that I'm working with subsets of all of matrices of all sizes over a given algebra with certain compatibility properties, namely that I can combine points clockwise like this. But what I'm doing here is that I'm restricting somehow to a finite, to a certain dimension. So I'm not going beyond a certain dimension. And this is what I mean by truncating things. But apart from this limitation of the dimension, it's precise. These are precisely the same definitions that one knows from non-commutative function theory. And one particular example, which will be important in the sequel, is that of the upper half plane. So here I'm just considering the A-valued upper half planes in MK of A for certain dimensions K at once. So this is the matrix valued upper half plane then. And then you define precisely, as you do it in the usual setting, what a non-commutative function is. But here again, with the limitation of the height, I'm just saying that these usual properties, namely that we have compatibility under this clockwise addition, let's say, and we have this compatibility under similarity, that this again is limited to sets up to a certain dimension. But apart from this limitation, these are exactly the same properties. And again, we can talk about continuous functions or continuous non-commutative functions of a certain height if the level functions, so the functions defined on the level sets, are continuous in the respective operator norm topologies. So again, this is the usual setup. The only difference is that we truncate somehow the dimension of matrices that we consider. And the reason for this is the following. So remember that we had this Dyson equation, and whenever there's a positive map, we can consider the unique solution, the holomorphic function, being the solution of the Dyson equation. And if eta is k positive, we can consider this Dyson equation on every level, namely on every k by k on every k by k level, let's say, for every eta k, and this gives me for every k from 1 to n, if the eta is an n positive map, a function from the k by k, from the upper half plane over the k by k matrices over B to the lower upper half plane over the k by k matrices over B, which satisfies the so-called, the kind of amplified Dyson equation. And then the observation is that these functions together, so if you just take these abstract solutions of the Dyson equation and combine them level for level to a function from the non-commutative set of height A, n given by the upper half planes, then it combines to a non-commutative function in this sense. So this, but we can only consider it up to level n because the eta fails to, is only assumed to be an eta, to be an n positive map. So we can only consider it up to this level. So this is why we need this particular limitation. And in fact, it's already interesting, as you know, in the case of two positive, or in the case of non-commutative functions of height 2, because then you can already go one step up, and you have tools. You have the usual trick available, which allows you to compute basically the non-commutative, basically the Fréchet derivative in terms of evaluation. So this is the crucial observation here, that still this trick, which underlies non-commutative function theory, still works in this two positive case. This again is not surprising for people who know about non-commutative function theory, but it's important here because now we can apply this result to the Cauchy transforms for a two positive map, and it simply means that we get access to the non-commutative. That we get access to the Fréchet derivative of our Cauchy transform just by evaluating the Cauchy transform, this function g, for the amplification of eta. And this is why now you should see why it is actually important to have the two positivity available, because then we can go up one step. We have still a kind of Cauchy transform, which has nice analytic properties, and we can use these nice properties to derive properties of the derivative. And this is precisely what we do. I mean, because I'm slowly running out of time, let me just give this concrete application, namely this lemma here, which was basically obtained by Scherban-Belinsky, and some reformulation was done by me. It simply characterizes elements in the 2x2 upper half plane in terms of some norm conditions. And with these properties, we can actually use the insight that we had on the previous slide to derive bounds for the Cauchy transform. So here are the implications that we are interested in. So we know if this condition is satisfied, this particular point here lies in the 2x2 upper half plane. And the other way around, if I know that my B lies in the upper half plane, I have this bound here. And the H sits exactly at the position where the derivative shows up. So this quantity here, this bound here, will give me a bound for the Fréchet derivative of my Cauchy transform. And here it comes. This again appeared already in some particular, or in some more restrictive setting in the work of Scherban-Belinsky. And the statement is that the Fréchet derivative of my solution of the Dyson equation in the case of two positive maps can be bounded like this by the imaginary part of b to the power -1 norm squared. And this is a little bit more technical. You will certainly not see directly why this is important, but it's actually quite important because this particular bound here, which involves the phi in addition, the state phi, which was specified on my algebra B, because this one allows you to perform this integration, which appeared in the formula for the Levy distance. So that one has such a bound is actually a very important thing in order to carry out the computation. And then we can actually go a little bit further and study properties of these solutions of the Dyson equation and the properties that we need in order to follow the proof strategy, which I outlined at the beginning, are some joint continuity properties. And what I'm saying here is that now I'm looking at my function as a function, these g etas, as a function of two arguments, namely the eta argument and the point in the upper half plane. And in fact, one has some uniform limit like this. And this implies that one has continuity, joint continuity in both arguments of the function g. And at the same time, one has also joint continuity for the Fréchet derivative of this function. And this is one crucial ingredient that one can prove using these insights about the Fréchet derivative. And the second one, this is the operator valued implicit Burger's equation. And this allows you to study the dynamics, let's say, of the Cauchy transforms if you perturb the completely positive or the positive map, in this case a two positive map. So we start with a C1 path, and then we look at somehow the function, the solution of the Dyson equation depending on T and on B at the same time. And again, we obtain a joint continuity of this function, also a joint continuity for the derivative. And what is interesting is that the dynamics, the time derivative, let's say, of this function here satisfies this equation here. And this is what is called, well, what we call the operator valued implicit Burger's equation. In the scalar valued case, this appeared in the early work of Voiculescu. In the previous version, in the operator valued case, appeared in the work of Angelevich, Belinci, Fevrier, and Nika. But this was in a much more restrictive setting than here. And these tools together allow you to prove the statement. And with this, I come to the end. Here, I just summarize the results that we have. We obtained the separate Hölder continuity and a uniform continuity of this map by establishing all these properties. But now I'm definitely over time. I thank you for your attention.
Thank you very much, Tobias. Wonderful talk. Questions, comments, suggestions? Well, if there are no questions, let's thank Tobias again.